Okay, so this is the last video for the first section of notes, and this kind of leaks into topic 2. So um, let me just get this one done, and then I'll start the topic 2 videos. We're going to talk here about subgroups. So G is a group, and so I'm going to use the times notation. I'm going to use E for the identity. Just keep in mind that sometimes we use plus, sometimes we use composition. There's various symbols we might use. With the multiplication type symbol, we often write GH, where we really should be writing G dot H, right? But that makes, just like we do when we multiply numbers and variables and stuff, right? So that's kind of useful. And we use G inverse, right? We do not use 1 over G, because that would just be confusing. I think I've talked about that before, mainly because we don't have commutativity. Now we're here, the situation we're in now is we have some H, which is a subset of G, okay? H is a subgroup of G, so subgroup, if and only if. Basically, so I'm going to write it like this: H dot E is itself a group, is a group. Now, this doesn't quite make sense. Okay, so I'll say what it is that doesn't quite make sense here. The dot, right, is really a function from G cross G to G, right? It's a binary operation on G. And so here what I what I really mean is dot restricted to H cross H, right? So this would be a function. I mean, in general, it would be a function from H cross H to G, because G is where this function is going. But to be a subgroup, we need this to actually go into H, right? So instead of having G here, we actually do need to have H here. So that the way we say that is we say H is closed under this operation. So we'll make that clear in just a minute. The other thing is we have to assume E, right, is in H. Let's see, okay, well, I mean, let's just sort of talk about what you need to prove. I mean, so this is what we need to show, right? That it's a subgroup, or sorry, that it is itself a group, right? To show that, we need to show that E is an H, okay? Because a group has to have the identity element, and we know the identity element's unique, so it's got to be that. So we should be a little careful. Later on, when we do rings, we'll see that that's what I'm saying there isn't quite true. Like, you could have a subgroup that has its own identity element that's actually different from the identity element of the group itself. Let's see if I can think of an example. Yeah, I do have an example, so I'll mention that right after I'm done with this. The second thing here is that we need this closure, right? So we need for all H, H prime and H, H prime is also an element of H, right? So it can't just be in G, it's got to actually be in H when we multiply. And 3, we need that for all H and H. H inverse is in H, so we need the inverses in there too. So we need to check those things. Now there is some ways of turning this into 2 things instead of 3 things in general, but I'll leave that up to you. This is what we want to check. Why don't we have to check other things? Like, why don't we have to check associativity, for example? So notice that associativity has this form. It has the form for all A, B, C. A, B, C equals A, B, C, right? And in particular, it's got this just a universal quantifier up front, okay? So if that holds in G, it actually holds in any subset of G, because this is just for everything, right? So if I take any S subset of G, it doesn't even need to be a subgroup. this equality would hold. Even if these things themselves are not in S, right, this equality would still hold. So the fact that this is a universal sentence, right, so this is a universal quantifier over something which is just, basically an equality, right, means that if it holds in the larger group, it holds in any subset, actually. Same thing if G were commutative, right? That would look like for all AB, AB equals BA, right? So this doesn't have to hold, but if it did hold, right, then it would also hold in every subset, because same argument, right? Because that's just universal again, okay? So we really just need to show these closure things up here. Kind of fun. There's one sort of interesting case that's worth thinking about. So maybe one definition. So if H is finite, or say if G is finite, let's see what I want to say. I don't want to quite say that. So if, oh, sorry, one more thing before I do this. If H subset of G is a subgroup, so I don't want to write this out all the time, then we write H. So this less than symbol, sort of G, right? So that's actually what we'll write. So this means subgroup. So it means that H is a subset, and H is closed under the operation, and it's closed under inverses, and it has the identity. So all that stuff. So it is a group itself. So here's the kind of fun fact. So if H is a subgroup of G, and H is finite, I'll just write H is less than infinity. Okay, maybe this is kind of bad notation in a way, but this means the size of H. Sometimes it's called the order of H, but it could be infinite, right? Like Z is an infinite group. Could be finite, like Zn is finite. Dn, all those sort of things. So if, let's see, I didn't want to write this. I want to say H is a subset of G. Not even going to assume it's a subgroup yet, and H is finite. Then H closed under the dot of G will imply H is a subgroup. So we don't even need to check inverses. We're going to get that for free. And let's see, just to be careful, I guess I need that E is in there, but I could get away here with just saying H is not empty. So let me just write this slightly differently. So let's say that we have a subset, and we have that 0 is less than, so there's something in H. It's not empty, is less than infinity, right? So we're in that kind of case, right? In that case, all we need to do is check closure under the operation, and we get the rest for free. And so the main thing is to show that inverses are in there. And here's how we do that. This is kind of fun. So let H be an element of this H. Remember, all I'm assuming right now is it's a subset. Consider, and I haven't defined this yet, so let me just quickly define it in this case, the cyclic group determined by H, right? So this is going to be just iterates of H. So this will equal HI. Usually this would be I in Z, right? Okay, but in fact, because H is finite, right, this is actually finite, right? So what we actually get is this. Let's just go through this since H is finite. We're going to get some n. There is some n. Least n. There is a least n. Hold on. Okay, let's see. Since H is finite, there is a least n such that if we look at this sequence here, so it'll be H, H2, Hn, right? So this can't go on forever because H is finite, right? So we're going to have, unique things up until we get so that Hn is equal to some Hk for, so this starts at 1, right? H1 for 1 less than or equal to k less than n, right? So in other words, we've got to have a repeat eventually. So they're all unique. We hit this thing and it has to be something back in this sequence, right? And what we're actually going to show is that the Hn has to actually just be H itself, right? So that's what we're going to show. Suppose Hn equals Hk, okay? Then what I can do is now we're going to sort of hop back out to G, right? I can multiply both sides by H minus k. Remember, this k is less than n, right? So we can multiply both sides by H minus k. So we get then H in minus k is equal to, actually, let me make it, let's do H minus k minus 1, right? So I don't want to get rid of them all. I want to say equal to H, right? So I'm going to be like that. Okay. If n minus k minus 1, let's see, does not equal 1, right? What do I want to say here? Sorry, if k does not equal 1, let's take that away. If k does not equal to 1, right, then we actually get a shorter sequence. We'll get H H n minus k minus 1, right? So this is actually a shorter sequence than this one, right? But the point was that the way we chose it is we chose in least, right? So this can't happen. This can't be shorter, right? So this, in other words, I guess what I'm really saying is this has to just be equal to n, right? Because n was chosen minimal, okay? But that tells me that k has to equal 1, right? So I guess here I'm saying suppose k doesn't equal 1, so I'll get a contradiction in this case. I guess I could have avoided that. So, right, what we get is that Hn equals H, right? And so Hn minus 1 equals E, right? And what we actually end up having then is we have that, we end up with this kind of sequence. We end up with E, H, dot, H. Let's see. What should I have done here? I should have done something slightly different. I guess just to make this, so let's take inly such that we have a plus 1 here. Sorry, I'm just going to change the indexing a little bit. So here I'll have n plus 1. This is just so things work out. This will be n plus 1, so this will be n. So we'll have Hn equals E, and then our set here will be H, E, H, up through Hn minus 1, right? So, and here we're just iterating H, powers of H. So this is what we call H, right? Okay, so this is the cyclic subgroup generated by H. And it looks, this is going to be just essentially the same as Zn here, right? Now Zn is an additive, not multiplicative group, so you have to sort of change back and forth between plus and times, but the point is, when you multiply two things, you add the exponents, right? So that's where we're getting the additive structure. And you can visualize this group here as, E, and then we move to H, you move to H squared, right? You just keep going around, and you get Hn minus 1, and you get back to E, right? So this is often called Cn2 because it's a cyclic group of size n, and all of those are essentially the same group. They just somehow labeled differently. I mean, they may be genuinely different objects, but they're all look the same. We'll talk about isomorphism later, and so we'll be able to make that more clear. But the point is, right, when we do this, because of this, right, we see that hn minus 1, we see that h times hn minus 1 equals e. Remember that our set was closed under products, so this h to the n minus 1 is an element of h, right? And it's the inverse of h, right? So we actually get the inverse for free, okay? So there's lots of stuff that happened here. So as long as we're in a finite group, h, so all we need if we have h subset of g, and h is closed under the operation, right? Then if we have h and h, we get that h, usually we would say that the subgroup generated by h would have to be the set of all, no, so here I'm in a situation where h is finite, right? And so this would usually be the set of all hi, I, and z, right? But it turns out we don't need all that. It's really the same as hi, I, and z, you know, let's say, so in, I'm using in there, maybe that's bad. Let me call this something else. Let me call this k, okay? So that turns out to be that this is just hi, I, and z in, right? So we just need in many things. So this thing has size in. Let's see. So in this, so this is a, so first of all, this is a subgroup because H had an inverse, but also anytime we take a single element and generate from it like this, right? I'm going to talk about generators in a minute, but we generate from it like this. This is also a subgroup. So this would be a subgroup of H, and it would be a subgroup of G. It's the cyclic subgroup generated by H, right? And we actually say the order here, right? The order of H is the size of this subgroup. And here we're saying that's n, right? So this is just notation. This is how we denote that. And so we say H has order n. Okay, cyclic groups is going to be what the first chapter of topic 2 is going to be all about. So we'll talk more about these things later. But right now, these are just subgroups is all we're looking at. Let's see, one other thing along these lines. Let's look at generating. So if I have S subset of G, yeah, I mean, sort of should look at ways of generating subgroups, right? So now here's just a subset. It's not necessarily a group, okay? Then I want to talk about the subgroup generated by S. And there's going to be two definitions for this. So one of these is top down. So it's going to be the intersection of the set of all H, such that S is a subset of H, is a subgroup of G. Okay. And again, it's pretty clear that, I mean, so I'll talk through it, and I guess I'll write out one of these carefully just to show you how the quantifiers go. But the intersection of any collection of subgroups is itself a subgroup. Okay, so this thing is a subgroup of G. I need to show that. But because of that, and clearly S is a subset of this intersection because S is a subset of everything we're intersecting, right? So once we know it's a subgroup, we know that this is the smallest subgroup that contains S. So that's why we call it the subgroup generated by S. Now, this description doesn't tell us how things in here are generated by objects in S, so we'll have another description that makes that more clear. But for this, let's just see, for example, that this thing here, right, is actually closed under the operation of G, right? And so here I'm going to just write out the quantifiers. I want to say take two things in H, right? So I'm going to say for all H prime, sorry, let's see, in here, right? In here, oh, sorry, I mean, I don't need to say for all there. So let's do it like this. So let H prime be an element of this, right? We want to show that H prime, the product, is in that. Then we have, okay, we have that for all H, S subset of H subgroup of G implies H prime are an element of H, because this is just the intersection of all those things. This, of course, implies for all H, S subset of H, subgroup of G. Now this is a subgroup, right? It implies that H prime is an element of H, right? But again, this is for all H, right? So this implies that H prime is an element of H, right? So we see that, so we see that this thing is closed under the operation, right? Same sort of argument for, E is in every one of these, so E is in that. Not in S, but in this generated thing. Inverse is same thing, right? If I take something in here, it is in every one of these, so the inverse is in every one of these, so the inverse is in there, right? So simple arguments. What's another way of generating S? So it's also true that this holds. So S is also equal to the set of all S1 N1 dot SK NK, such that Si is an element of S and Ni is an element of Z. Okay, so let's notice that, first of all, with this so this is a different definition than above, right? But I'm going to show that this is also the smallest group containing S, and then we'll know that these two definitions are actually the same. So first of all, we have that E. Let's see, the one thing I need to assume here, and probably just should have said it right at the beginning, is I should have said not empty. All right, let's just make S not empty. So E is equal to S to the 0 for any S and S, right? So E is definitely in here because something is in there, and so S to the 0 is in there, okay? And 2, take two things in here. Let's take S bar and T bar in S. Okay, then what do I know about those things? I know that S bar is equal to S1 N1 SK NK. I know that T bar is equal to T1 M1 TL ML, right, where these SI T I are in S, right? And then when I look at S bar, T bar, of course, then I'm just sitting these next to each other. So this is just S1 M1, SK MK, T1 M1, TL ML, right? That's clearly also just a product of powers of things. So this is an S, right? So we do have closure. So if I take two things which are in there under this description up here, right, then I get this thing, right, which is another thing which is in there, right? So this is closed under products. And 3, if S bar is in here, right? So S bar equals, S1 N1 SK NK. Then we see that S bar inverse is equal to SK minus NK, not S1 minus N1. Right, and so that is also just a product of powers of things in S, so this is also in S, right? Okay, good. So we have closure under inverses, closure under product, and E is in there, so S is definitely, so we've shown, therefore, right, S is a subgroup of G, right? And it's clear that everything in S is in here, right? So S in S implies S1, so that's a power of something in S is in S, right? So we know that S is a subset of this, right? And we also know that if H contains S, and this is a subgroup of G, right? So we're looking at one of those things, then clearly S1 N1 SK NK is an element of H, right? Because H is closed under the product, right? And inverses and stuff. These NIs are in Z, so they could be negative, so I do need the inverses. And so it's just got, oh, I see. Okay, so yeah, so so S is contained in H. That's all I wanted to say, right? And so I see here that the current version of S, defined this way, right? So I guess what I have is this. I have the thing I'm defining here, S1, N1, dot, 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 SK, NK, the products of powers of things in S. So SI and S, NI and Z, right, is contained in the intersection of the set of all H, such that S is contained in H is a subgroup of G, right? So this is contained in that, but this is a subgroup. We just showed that. So in fact, we must have equality here because this would be one of the subgroups which are in there, right? So we must actually have equality there, holds, right? And so either definition we use is how we define what the group generated by S is. So the things in here would be the generators maybe, right? Okay, so that's an important construction. So there's two main facts. So one is just this construction. By the way, these things here are just called words. I mean, if we just take symbols from an alphabet, right? I can just take any alphabet at all. And by alphabet, I really just mean set, right? I just have a set, right? And I can define a word from this set to be just something of this form, x1 to the n1, dot, 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 xk to the nk. And this is just a completely formal thing. These are things from X. These are elements of Z, right? So it's just this thing, and this is a word, right? And if I take two words and I set them next to each other, I get a word, right? So we get something called the free group over X generated this way. So it's a really easy way, really important way actually to generate groups with not much nice structure. I mean, they're very nice groups in a way. They're kind of like vector spaces in a way. Because they're free objects. I mean, I'm not going to get into that, but in other words, they're completely determined by X, right? Sort of like a vector space is completely determined by its basis. But that's sort of what these are. I mean, these are kind of the words, right? Now, you can reduce words. Like, for example, if I have something like x1, 5, x1 minus 3, so that's a word, right? But I can obviously replace it with x2, x1, 2, right? So it's just x1 squared because, the usual rules of exponents will hold. So this is a word, this would be a reduced word, right? Or if I have something like x1 inverse e x2, right? Well, the reduced word would be x1 inverse x2, right? Things like that. Okay, so we have that kind of thing. What else do I want to talk about here? I guess that's about it here. I mean, in the notes, I talk about the centralizer and the center of Z, and I have a relationship between these two. I'll just let you look at that. Later on, I don't know that we really use them that much in the class. These come up a lot in, for example, in the silo theorems, which I do have notes on, but they're not an official part of the class. But anyway, you can just read those there. But they're interesting subgroups. And I'll go ahead and stop the video there.